So here we are. We have finally reached probability with chapter 13, this is the one I missed. It's level 13.3. I know some of you will be upset with me about this. Sorry about that. Level 13.3 probability. So you have seen probability here and there. Examples of probabilities you've seen: tossing a fair coin, rolling a fair die, picking a card at random. We have determined what the probabilities of each of those are because we know certain things. So in order to get into this, we need a couple vocabulary terms. Probability model is all possible outcomes. The sample space is a simple way of saying the set of all elements that represent all of the possibilities. This is the set of all possible all possible outcomes. And we say outcomes are just one result. So we got probability model, we got sample space, we've got outcomes. So the definition of a probability model with a sample space S, where each of these is an element. So the probability, in order for something to be a probability model, the probability of each element happening has to be non-negative, which means it's greater than or equal to 0, and the sum of all probabilities is equal to 1. So in general, when we talk about a probability, it's going to be less than or equal to 1. If the probability is 1, it's happening. It's guaranteed. So if we look at this first example, so it says a bag of M&Ms, the candies are colored red, green, blue, brown, yellow, and orange. Suppose that a candy is drawn from a bag. I've given you 4 of these. Determine if each one of these is a probability model. So we have to check if it is non-negative and that it adds up to 1. So if I have 0.3, 1.5, or 0.15 and 0.15 is 0.6, 0, 0.8, 1. So A is, if we look at B, all of these are non-negative. 1, 2, 3, 7, 9, 1.2. This is not, because all of these add up to be greater than 1. If I look at C, green can't be negative, so it's not. Even if it does total up to be 1, it can't be not a negative probability. That doesn't make any sense. Lastly, D, that means you just have a bag of yellow M&Ms. So this is yes. All right, flip it over. Okay, so example 2. Experiment is rolling a fair die. A die is a cube having 1, 2, 3, 4, 5, 6. We've done this plenty of times. Construct a probability model. So that means I want to know all the possible outcomes. So what's the probability of a 1 happening? What's the probability of 2 happening? What's the probability of 3 happening? Well, that's 1 out of a total of 6. 1 out of a total of 6. 1 out of a total of 6. Probability of a 4 happening is a 1 out of a total of 6. Probability of a 5 happening is a 1 out of a total of 6. The probability of a 6 happening, hopefully this is getting repetitive, is a 1 out of probability of a 6 happening. Okay? How about an experiment consists of tossing a coin? The coin is weighted so that heads is 3 times as likely as tails occurring. So the probability of tails is, let's say, x. The probability of heads, therefore, would be 3x. And we know that x plus 3x is equal to 1, because the probability of both of these should add up to 1. So we have 4x equals 1, or x equals 1/4. So that means that the probability of a tails happening is 1/4, and the probability of a head happening is 3/4. Those both add up to 1. This is our probability model for this weighted flip, or weighted coin toss. Next thing, we're going to be saying an event occurs and the probability of an event that happens. So an event is a one-time deal. We can have multiple events, which means we have the same experiment happening over and over and over again. So an experiment has n equally likely outcomes if the number of ways that event E can occur is m, then the probability of E is written here, number of ways E can occur, which is m, over the number of possible outcomes, which is n. So if S is the sample space, then we have the number of elements, probability of E is the number of E over the number of S. Okay. You might know this already. Calculate the probability that in a 3-child family, there are 2 boys and 1 girl. Assume that all of this is equally likely. So you read this. What are the chances that all of these could happen? Well, first off, just start listing these out. What are the different ways you could have? We could have boy, boy, boy. You could have boy, boy, girl. You could have boy, girl, boy. You could have girl, boy, boy. You could have boy, girl, girl. You could have girl, boy, girl. You could have girl, girl, boy. You could have girl, girl, girl. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 total outcomes for this. We could also have done this. This is 2 to the third, right? There's 2 things, 3 ways. 2 to the third gives us 8 different outcomes. How many times do we have 2 boys? We have 1, 2, 3. So the probability of 2 boys, 1 girl is 3 out of 8. Because we look at the number of ways 2 boys and 1 girl can happen, which is 3, and the number in the total in the sample space, which is 8, and that's how we get this. So as easy as counting for us. Okay, flip it over. Okay, so with example 5, it says, consider experimenting with a single fair die. So we got 1 die. Let E represent roll an odd number. Let F represent roll a 1 or a 2. Write event E and event F. So E is roll an odd. We have 1, 3, 5. F is a 1 or a 2. What's the number in E and F? Remember that symbol is and. Well, we look at what's in common. That's 1. Write E and F. What is N of E or F? E or F, if we look at it, is 1, 2, 3, 5, because now we include that. So an E or F is 4. What's the probability of E happening? So the probability of E is 3 out of 6, which is 1/2. The probability of F happening, which is 2 out of 6, or 1/3 happening. What's the probability of E and F happening? Well, that's just 1 out of 6 because you'd be a 1. What's the probability of E or F happening? Well, that's 4 out of 6, or 2/3. So these first 2 questions are kind of building up to giving us all of the number sense that we would to get here. Likewise, if we have probability of E is given as 0.2, and the probability of F is given as 0.3, and the probability of E and F is 0.1. This is exactly like we had before. Find the probability of E or F. So if we have the probability of E happening, that's 0.2. I want to know P, probability of E or F. Well, probability is 0.2 of E happening is 0.2. Probability of F happening is 0.3. And I'm going to take away the overlap. So the probability that these happen is 0.4. We call these mutually exclusive events. So events that are mutually exclusive have no overlap. If this formula looks familiar, this is what happens when we were counting before. So if there is overlap, we have to subtract it. Find the probability of E or F, i.e. find this, which is what we did. If things are mutually exclusive, that means they have no overlap. It's like saying, if I flip a coin and roll a die, what's the probability of getting a heads or a 1? Well, they don't affect each other, so we add the probability. So with example 7, it says E is 0.4, F is 0.25, E and F are mutually exclusive. Mutually exclusive. Find E or F. Probability of E or F happening is just 0.4 plus 0.25, which is 0.65, which is definitely less than 1. The last kind of interesting number that I want you to see is something called the complement. So computing the complement, which often is written with this line over the top, it just means that something is not happening. So if you can compute the way something does happen, you can figure out how often it would not happen, which is just 1 minus its probability. Now that may seem easy, but we often use finding the complement to figure out what the probability of something actually happening is, and we're going to see that on the last page. With example 8, it's going to start out easy, and then we're going to use the same logic for example 9, and then it's going to hopefully blow your brain a little bit. So, on the local weather news, it says the chances of rain, or the probability it rains tomorrow, is 40%. What is the probability it will not rain? Well, 1 minus 0.4 probability of, that's our notation, not rain, is equal to 1 minus 0.4, which is 0.6, or 60% no rain. Now that's not that bad. This is where it actually gets tricky. What is the probability in the group of 10 people that at least 2 people have the same birthday? Assume that there are 365 days in the year, because obviously there are leap years. And then we're going to do, what about a group of 23? What about in a group of 30? So this is what we're going to do. We are going to first find probability of people don't share a birthday. And if we know the probability that people don't share a birthday, find the complement. Because the complement would be how many people share a birthday. Okay. So if you have 10 people lined up, 5, 6, 7, 8, 9, 10, each of them have 365 days to choose from, right? 365, 365, 365. That's 365 to the 10th power. That's a big number. This is our sample space. Okay. Well, if I have, let's say the first person picks their birthday, and we're finding out the probability that they don't share. So then the next person would be 364. Then the next person would be 363. Then the next person would be 362. Then the next person would be 361. Then the next one would be 360, because we're going down until they don't share a birthday, right? Then 359, then 358, then 357, then 356. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All over 365 to the 10th power. Now, if you're saying to yourself, wow, this looks like a permutation. It is, because this order matters. We could write this as, in our calculator, 365, choose 10, or permute 10, over 365 to the 10th. Let's do that. So we go menu, probability, permutation. We have 365, comma, 10, divided by 365 to the 10th. And I get this really weird decimal. I want 1 minus that. This is the probability. 88.3% chance people don't share a birthday. That means there's a 11% chance. So let me zoom out. So this number, probability not share, equals about 0.883. Therefore, the probability that people share is 1 minus 0.883, which is 11.7% chance that 2 people share in a group of 10. So now if you extrapolate that, that's A, and we do B, probability in a group of 23, then that would be, I'm going to just write it N permute R of 365, choose 23 over 365 to the 10th, and we're going to do 1 minus that. So if I go here and I go 1 minus permutation, 365, choose 23 people over 365 to the 10th, and I hit Control Enter. So as it turns out, the probability of a 23 happening is about 50.7% chance happening. And if we did this, the probability of a group of 30 would be about 70% likelihood. Now, I know I'm pulling these calculations, but I know you guys can do this just as easily if we wrote it all out. So, this is the end. I will be giving you guys your take-home test, and then you are done with math for high school. Thank you very much.